You folded your phone in half this morning. You opened it. You folded it again. The screen is glass. Actual glass. Not plastic. Glass doesn't bend. Glass breaks. Everyone knows this. Samsung's Galaxy Z Fold has glass that bends to a radius of 1.4 millimeters. That's tighter than a pen cap. The glass is 30 micrometers thick, thinner than a human hair. It needs to survive 150,000 folds. That's 5 years of folding it 30 times a day. The engineering required to make glass bend without shattering defied everything we knew about material science. This is how they broke the rules. Before 2019, every foldable phone used plastic screens. Plastic bends easily. It also scratches if you breathe on it wrong. You could feel the crease with your finger. It looked cheap. It felt cheap. Samsung wanted glass, real glass, the glass that protects normal phones. Gorilla Glass can't fold. It's too thick, too rigid. The molecular structure won't allow it. So Samsung needed to engineer a new type of glass, ultra-thin glass. UTG, 30 micrometers thick. For context, regular Gorilla Glass is 400 micrometers. They needed to make it 13 times thinner and somehow keep it strong enough to survive years of bending. The hinge was the other problem. It needed to fold perfectly flat, no gaps, no wobble, with precision measured in micrometers. One misalignment and the glass shatters. Here's what they did. They started with standard glass. Then they heated it and stretched it, like pulling taffy. The glass gets thinner as it stretches. They kept pulling until it reached 30 micrometers. At this thickness, glass behaves differently. It's still rigid at the molecular level, but it's thin enough that it can bend slightly before the internal stress breaks the molecular bonds. The trick was the bend radius. Bend it too tight and it snaps. Samsung engineered a hinge that limits the bend to exactly 1.4 millimeters radius. Not 1.3. Not 1.5. Exactly 1.4. This gives the glass just enough room to flex without fracturing. Now here's the insane part. The hinge contains over 150 individual components. Tiny gears, springs, cams, all working together to control the fold. When you close the phone, those components guide the glass through a precise curve. The hinge creates what they call a water drop fold. The glass doesn't crease sharply. It curves gradually. This distributes the stress across a wider area instead of concentrating it at one point. 150,000 folds tested. That's folding it closed, opening it, closing it again, over and over, 30 times a day for 5 years. Samsung manufactures UTG in South Korea using modified LCD production lines. The glass starts as molten silica. They pour it onto drums that spin at controlled speeds. The spinning stretches the glass as it cools. Temperature control is critical. Too hot and the glass is too soft. Too cold and it breaks during stretching. They hold temperature within 5 degrees across the entire sheet. The sheets are massive. Multiple phone screens cut from each one, but the yield rate is brutal. Maybe 60% survives the cutting process. The rest develops micro-fractures and gets scrapped. The hinge assembly happens in clean rooms. Each hinge takes 20 minutes to assemble. Robots place most components, but humans inspect every hinge. They check that all 150 components move correctly. One stuck gear ruins the entire hinge. That 30 micrometer glass sits on top of a plastic support layer. The plastic is 20 micrometers thick, so the total screen is 50 micrometers. The plastic layer adds flexibility and prevents the glass from shattering completely if it does crack. It's a safety net. Below that sits the OLED display panel. This layer also needs to fold. OLED pixels are organic compounds deposited on a flexible substrate. They emit light when electricity passes through. Each pixel can bend independently. The display panel is 40 micrometers thick. Add it all up. Glass layer, plastic layer, OLED layer. You're at 90 micrometers total. Thinner than a strand of hair. But here's the challenge. All three layers need to fold at slightly different radii. The outer layer travels farther than the inner layer when you fold the phone. The hinge compensates for this. It creates a teardrop-shaped gap that allows each layer to fold at its optimal radius. Every major foldable phone uses some version of this technology now. Samsung's on their 5th generation. The Z Fold 5 weighs 253 grams. Barely heavier than a regular flagship phone. The screen is 7.6 inches when unfolded. It folds down to pocket size. Here's what this means for you. You're carrying a tablet that fits in your pocket. You can run 3 apps side by side. Watch videos on a screen bigger than most Kindles. When you're done, it folds in half. The technology everyone said was impossible 3 years ago is now normal. But there's still a compromise. That crease in the middle? You can see it. You can feel it. It's there because the glass has to bend. Physics hasn't changed. They just found the absolute limit of what glass can do. The crease is the price you pay for a foldable screen. Samsung didn't invent thin glass. They didn't invent flexible displays. What they invented was the combination, the understanding that you could push glass to its absolute physical limit if you controlled every other variable perfectly. The hinge isn't just a hinge, it's a precision instrument that protects the glass by controlling exactly how it bends. This closes something important. We started this series with Gorilla Glass, glass engineered to resist breaking. We're ending with UTG, glass engineered to bend on purpose. Both are solutions to the same problem. Make glass do something it shouldn't be able to do. The future is already being built. TSMC is using similar precision engineering to make AI chips. Thousands of manufacturing steps, each one controlled to the nanometer. That's where we're going next. Next time you fold your phone, think about those 150 hinge components. Think about glass stretched to 30 micrometers. Think about 150,000 test folds. Tomorrow, we're looking at NVIDIA's Blackwell chip, the manufacturing precision that makes AI possible.